Hi, my name is Jromero, and here is the result of my final project for Ecen 160. Quick overview, you can see we have a binary counter which counts in binary and sends a signal over to the prom for code, and where we have a set of instructions that are sent to 4 bits are sent to the instruction decoder. The other 4 bits are sent to the data mux, which according to the instructions need to adjust or change the registry file, which contains a set of registers. And we have the ALU, which does some addition using AND, OR, and XOR, and an addition of a add subtract subcircuit. And finally, there's a ASCII display, which interprets the information stored in the registry file by the ALU or directly into the ASCII display, and it depends on what it's stored there. It either store text, hexadecimal, or numbers. Basic instruction. The initial instructions are the first 3 are essentially sending information through the prom code to the decoder, and all essentially what they do is store the an H character in the register as an ASCII code, and then display the H into the TTY and Logisim. The first set of instructions convert the prom code to the ASCII display using the mux registry file in ALU to display hello BD or Brother Davis. Second set of instructions, compute the 3 plus 4 using the ALU and the registry file which stores the 3 and the 4, and compute the ALU then computes the result of 7. In the third set of instructions, add or multiply 3 plus 3 times 3 into the using the ALU. The fourth set of instructions would do the software subtraction of 4 minus 3, which results in 1. I had a little bit of a issue with the ALU in this aspect, where I had tied in the inputs where they're either on the A or B side, 0 through 3, and I had tied them in wrong. But once I troubleshot the inputs to the appropriate subcircuits of the AND, OR, and exclusive OR subcircuits, I was able to get the correct results. Initially, my results were 4 minus 3 equals 5, which triggered me to understand what was going on in the registry file, but come to find out it was the ALU. But I did learn a lot from troubleshooting this, where how the ALU actually computes, and even minor inappropriate connections do not give you the correct results. And the final set of instructions, the fifth instructions, does the exact same calculation, but instead uses the hardware subtraction inside the ALU, which is 4 minus 3 equals 1. Here on the left we have the prompt for code. Here we use the truth table to identify all the signals to be sent to the data mux, and the first set of instructions are set to the instruction decoder to send to additionally to the data mux register file in the ALU. The data mux itself consists of 8 bits as inputs, 4-bit output, and a selector to determine whether it will be sending the first set of bits or the second set. The register file consists of two 4-bit registers. Each of these 4-bit registers contains a 1-bit register, which also is composed of 2 to 1 mux and a D flip-flop. The ALU contains the add and subtract subcircuit, the OR, and an XOR circuits. They each feed into 4 to 1 muxes and additionally feed into the register. The add, subtract, OR, and an XOR gates subcircuits are as illustrated. The add subtract was a little bit of a trickier set of instructions where you have the four first set of bits that feed into the 1-bit adders, some 1-bit adders, and then the second set which feed into exclusive or XOR gates that serve the purpose of allowing the subcircuit to be flip-flopped using a subtractor bit feeding the XOR. So when the extractor bit is enabled or has a high volt feed, it'll flip-flop all the bits and then turn it into a subtraction. The ORs and XOR gates are essentially the same as our previous lessons.